let's first define electric flux. So in other words, this is going to be the definition of electric flux. A measure of the number of field lines poking into or out of a surface is the electric flux. So if I write out this detail here, we then say that electric flux is equal to the number of field lines poking through the surface. That is our definition. Mathematically, we then say that the electric flux, sometimes you'll see me write an E, is equal to E dot A. This is only true if E is a constant electric field, or I'm integrating over a closed surface of E dot dA. And even though I could use this for a non-constant field, I could also use it for a constant field and I get the exact same response. But typically, we then say that if you have a non-constant field, that's the way you do it. This is my definition of electric flux. Gauss's law shows there is a deep connection between electric flux and charge. And the way we've written it already is we then say that the flux is proportional to the enclosed charge inside the Gaussian. Now, in order to really understand how the role of flux and the enclosed charge, now note, I'm really talking about Gauss's law now. So what I'm really saying here is that let's physically understand how Gauss's laws work. And so there are three behaviors that will show the workings of Gauss's law. So one thing that we'll look at is the first one here is that we're going to say that the electric flux is proportional to the enclosed charge inside the Gaussian. 2. Electric charge or electric charges outside a Gaussian will not contribute to the flux. 3. Electric flux is independent of size and shape of the Gaussian. So look at that. I'm talking about flux and I'm talking about charge. I'm talking about shape and I'm talking about charges outside. All of this has to do with Gauss's law. So let's go look at the first one. So this lecture is going to be on the electric flux is proportional to the enclosed charge inside the Gaussian. So know that there's a lot of words here, and that's because we're defining things. But we will get to this where we'll be doing a lot of conceptual calculations in our head and then writing just down a few lines here. So here's the question that we want to talk about. So suppose a Gaussian contains some charge. Okay, so now here's the question. Can one determine how much and the sign of the enclosed charge without looking inside? And of course, the answer is absolutely yes. So before we answer this question, we need some references. So we need a reference that connects the number of field lines to charge. So one that we've used in the past, and I'll continue to do this, is that I imagine that I have a positive charge. So here's my positive charge. And what I said last time is I said, if we have a single positive charge, we were going to say that this was 4 lines pointing outwards. So in other words, I have field lines. So if I can see 4 field lines, then I know that it's a positive charge. By the same idea here, imagine that I have a negative charge. And in this negative charge, we're going to say that it has 2 negative charges. So in this situation, instead of 4 lines, we need 8 lines. But now these guys are coming into, it looks like they're coming into, but they start at the charge and then flow out. So in other words, if I have a charge of 2e, I'm going to say that this is equal to 8 lines pointing inwards. And that's our reference. So now, let's enclose each of these charges inside an opaque, or we could also say the word murky, spherical Gaussian. Now we gotta be careful here. So when I say spherical Gaussian, I really mean a spherical shell. So what do I mean by opaque or murky? That is, we cannot or can't see what's inside, right? So we cannot see what's inside. So that's an important point. So here we go. I know that if I have a Gaussian and I'm going to enclose it with that sphere right there. Now remember, I can't see inside of it. It's opaque. And I'm going to call this number 1, the smaller one, or this guy right here. So what do I see here? At the Gaussian surface, all I see is that I see 4 lines popping out. So once again, I can't see inside. And I could do the exact same thing with the other one. So in other words, if I take this guy and I do the exact same thing, I can't see inside, but the only thing that I do measure is that I have these field lines that are coming out of the Gaussian like this. Now, once again, we can count these field lines poking, not flowing, through the surface and make these assertions. So if I look at Gaussian number 1, what do I see here? Well, I'm looking at one right here. And if I look at the electric flux, what I see here is that I have 4 lines poking outwards. That immediately tells me, because of our reference, if I see 4 lines, that tells me then that the Q enclosed is, Q enclosed must then equal plus 1e. So the Gaussian is hiding what's inside, but we have to conclude that if we have 4 lines, then those 4 lines lead to the conclusion that it has to have a charge of 1 positive E. I can say the same thing about Gaussian too. So wait a minute, before I move on this, what does this really tells me here? So now, what does Gauss's law say? Gauss's law says that if I have an electric flux, this will be proportional to the enclosed charge. Or if I look at this counting wise, it just says that 4 lines poking out has to be 1 electric charge, 1 positive electric charge. We knew that already, but that's what Gauss's law is telling us. What if we didn't know what was in there? It has to be this way. So I'm going to do the exact same thing. I'm going to copy this, and then I'm just going to modify this for the Gaussian number 2. And this is only to make it faster, no other reason. So now we can see that this is 2. And then we now have green. Okay, so if I look at green, what I have here, I have 8 lines that are poking through the surface that point inwards. So in other words, I have 8 inward, right? 8 lines poking inwards. I immediately conclude that this now has minus 2e from our reference. And if I use Gauss's law, all this is telling me here is this. So if I look at this guy here, it's telling me this. It's telling me that I have that 8 lines is equivalent to 8 lines poking in, and this is equivalent to minus 2e. So by knowing the number of field lines, I know what the enclosed charges, even though I don't know what's going on. Now, just as an example, to keep playing, this game here of trying to count, field lines poking through, I want to give you an example here. As an example, I'm going to show you a cross section. So there's a cross section of a central ball and 2, let's say, metal shells. So what I'm thinking about here is that that central metal ball here has a charge on it. These have the following charges. So it says here that I have the first one I'm going to say is that I have one. We have that the central ball has charge Q. So if I draw this, I'm going to imagine that I have this here now. So if this is my ball here, I imagine that this is a red ball and this is positive, and I'm going to say that this guy has a charge Q. Now I have two metal shells. So if I look at these two metal shells here, then I'm going to say that the first one, I have a smaller shell has charge minus 3Q. So when I'm looking at this, I'm going to think about my shell here. And it's going to be thin, but I'm going to draw it just a little bit thicker to remind you that we're dealing with the shell. So now if I look at this metal shell, what you're seeing is that this guy has a charge of, in this case, I'm going to say it has a charge of minus 3Q. Then I have a third object, and this is going to be a larger shell with charge, in this case, of plus 5Q. So now I have to draw a larger one, and this is what we call concentric shells. Now I could have drawn these as lines, but again, I want to give the illusion that we're talking about shells. And then this guy here has a charge of 5Q. So what we want to do is this question. And I need to move this down because I'm going to run out of space. So question, what are the flux values at points R, 2R, 3R, which are Gaussians? Okay, so here we go. So when I look at this guy, we're going to pick two Gaussians, or three Gaussians, excuse me. What I'm going to do here is that I'm going to pick a Gaussian that's right here. And I'm going to say that from here to here, that's going to be a distance of R. Then I'm going to look at a Gaussian right here, and that's going to come all the way to here, and that's going to be 2R. And then I'm going to have a Gaussian out here, which is 3R, which then is something like that. So all we know here is that at these given locations, and what do I mean by locations? In this case, we're talking about R, 2R, 3R, the flux only depends on the enclosed charges. So let's look at the first one here. So what I imagine is that I have the first case I want to look at is that I want to look at the Gaussian at R. So when I look at the Gaussian here, all I'm doing here is that I'm enclosing a positive charge. And for the sake of simplicity, I'm going to say that the charge of this guy here is going to be plus E. So if I put my imaginary surface right in here, I know what the flux has to be. So that means here is that if I'm choosing this distance from here to here, and that's R, then according to Gauss's law here, it says that the flux at R has to be proportional to the enclosed charge at R, inside of R. And in this case, we're going to say that this is positive 1e. Therefore, my flux as a function of R will then be 4 outward lines. So that means at that Gaussian surface, I am going to see an electric field that is poking through the surface, and I have 4 lines. Now let's repeat the process for location at 2R. So now if I look at this guy, I have my Gaussian at 2R. So now what I'm going to do is that I'm actually going to copy this and modify it. So if I put this in here, what do I see here? Well, I see that I have some shells here, and I don't care about the inside one anymore. I only care about the one that's actually all the way down. So remember, I'm changing my Q values. So this is going to be minus 3e, and this is plus e. So now I'm going all around, and I'm enclosing all of the charges here. So what do I see here? What I see here is that my Q enclosed for 2R, I actually have minus 3e plus e, so this is now minus 2e. Therefore, that tells me that the flux at 2R has to be proportional to this Q enclosed of 2R. But if that's equal to minus 2e, that then tells us that the flux at 2R, using the same reference, I have to have 8 inward lines. So over here, we concluded that this had to be 4. Now we conclude that this guy has to have 8 inward lines. So then that means here that through this Gaussian, I'm going to have what? I'm going to have 1. There's 4, 6, 8. So that means I got 1, 2, 3, 4, 5, 6, 7, 8. So through that Gaussian, I now know that there has to be 8 field lines right there. So now let's repeat the same process here, where I'm now going to copy the whole thing and bring it down. And I'm going to say here that this is now our third situation, that this is the Gaussian at 3R. So drawing the sketch right here, so now I don't care about what's going on inside. I only care about if I've enclosed the whole thing. So now here goes my Gaussian. It encloses all of the three objects. So again, saying that I'm removing Q and I'm putting E instead so that we can use the same reference that we did before. So now I look at Q enclosed for 3R, and I'm seeing here that how much charge do I have? Well, I got plus E minus 3E plus 5E, and right away we could see here that that has to be 3E. This immediately tells us then that the flux of 3R must then be 12 outward lines, since Q enclosed is equal to 3E. So then if I was to draw them, then I got to draw 12, right? So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And of course, they're all pointing out. That's what Gauss's law is telling us.